Let us quickly have a recap of what we studied yesterday or discussed yesterday. So we started discussing uh, a brief about what static routing was, and static routing was used to create a routing table for a router, right? Because routing table is not automatically created for a router, unlike a switch, right? So using these two commands, IP route network, IP route the network, the address mask, and then we give either the next hop IP or the exit interface. Using these two commands, we can create the routing table of a router, right? So the problem with static routing was it is easy if we have, let's say that we have six routers in this diagram. We have six routers. So for every router that, let's say R1, R1 needs a connectivity. Okay, R1 needs a connectivity with R3, R4, R5, and R6. So R1 needs connectivity with four other routers, right? That means uh, there are six routers, right, connected in linear fashion, and R1 needs to have 40, not 44. So R1 needs to have four static routing command configured on its configuration line. Okay. Similarly, R2 needs such configuration. R3 will have such configuration. R4, R5, R6. All of them will have different lines of static route command configured on their router, right? Now, instead of seeing them connected in a linear fashion, if we have not just six routers, if we have, as I was giving the example, we have 100 routers, right? So, and they're not connected linearly. They're connected in a cross manner. All the routers are connected with each other. So it's a huge network of routers interconnected to each other. And typing static route command on each and every router based on the connectivity is an extremely tedious task, and we are prone to have human errors there. So we thought, why not create a protocol, or why not create protocols, right? So that it makes our work easier, and it will automatically populate the router's routing table and will also help the router forward data. For that purpose, we created dynamic routing protocol. Okay, dynamic means it automatically populates the router's routing table. So one of the routing protocols that we looked at yesterday was the OSPF, or the Open Shortest Path First. OSPF means OSPF open means open standard, meaning that any vendor router, it can be Cisco, HP, Aruba, Nokia, IBM, any vendor router can use this particular protocol. And these vendors can also communicate with each other using OSPF. There is no special there's no special feature required for different vendors to talk using OSPF, right? And there are Cisco proprietary protocols like ISIS. ISIS is Cisco proprietary. It means that only Cisco device can run ISIS. No other devices or no other vendor devices can run ISIS. That's what Cisco proprietary is. Then the shortest path first. Shortest path first is an algorithm which is called as the Dijkstra algorithm, right? And this algorithm is used everywhere. Even in real life, it is used everywhere. Right? And the work of a shortest path first algorithm, or the Dijkstra algorithm, is to find the shortest path from the source to destination. The Google Maps, in real time, we use Google Maps, right? When we type from and to in the Google Maps search bar, right? And when we ask it to search for the direction, right, it gives us the best path. How is it giving the best path? It is using this algorithm, Dijkstra algorithm, okay, to help us find the shortest path from source to destination. And Google Maps uses a lot of parameters. It uses traffic, it uses it uses road lanes, number of lanes, 2 lane, 2 lane, 3 lane, 4 lane, 5 lane, etc. All that, right? The traffic, the time, right? The terrain, is it a hilly terrain? Is it a normal terrain, etc. It takes all these things into consideration and gives us the best path. Similarly, OSPF also uses Dijkstra algorithm, but the parameter that it uses to calculate the shortest path is the link bandwidth. Okay. Then OSPF is a layer 3 protocol. OSPF is a layer 3 protocol. It uses a multicast address of 224.0.0.5 and 0.6. It runs on the IP number 89. And then we started a discussion that the OSPF runs on router interfaces. OSPF runs on router interfaces. And yesterday I said, please remember this particular statement. Okay. Then OSPF considers three types of interfaces. Okay. OSPF runs on three types of interfaces, or OSPF considers three types of interfaces. First is a serial link, then the other is an Ethernet link, and then we have a loopback, loopback IP or a loopback interface. Ethernet interface, serial interface, or a loopback interface. So in our previous discussions, earlier discussions before this particular session, we had discussed only Ethernet interface like fast Ethernet, gigabit Ethernet, 100 gigabit Ethernet. So during our discussion on spanning tree protocol, we had discussed these different links and their speed. So the serial interface is another kind of an interface which has a dedicated speed of 64 kbps. And a serial link is called as a point-to-point link. And in yesterday's class, we discussed why is it called a point-to-point. Then we have an Ethernet interface, which is also called as a LAN interface, right? And many devices or a range of devices or a range of subnet or interfaces can be configured on an Ethernet interface. We had also discussed. And in yesterday's class at length, we discussed what a loopback is. Loopback is a kind of an imaginary IP address. Okay, it's a virtual IP address for a particular router. Okay, and we discussed it can be thought of as a nickname for the router, right? And we discussed different scenarios of how to think of a loopback address. Okay, we discussed all that thing in yesterday's class. So continuing with yesterday's discussion, as I said, there are three types of interfaces. The first is a serial interface. The second is the Ethernet interface, and the third is the loopback interface. So OSPF, as I said, OSPF runs on the interfaces, router interfaces, not on the whole router. It runs on the router interfaces. So today, okay, so how it runs, let's see that. OSPF considers serial interface. Okay, in OSPF term, OSPF considers serial interface as a point-to-point interface. It considers it as a point-to-point interface, and we also discussed serial interface is also generally thought of as a point-to-point interface, and OSPF also looks at serial interface as a point-to-point interface. It looks at Ethernet interface as a broadcast interface. When I say broadcast, it does not mean the broadcast IP of 255, 255, 255. No. OSPF does not think Ethernet interface as broadcast in this sense. No, it does not think of it as a broadcast. When, from OSPF's perspective, Ethernet interface is a broadcast interface wherein that particular interface, for example, fast Ethernet 0/0 is an Ethernet interface, and for OSPF, this interface is a broadcast interface. From OSPF's perspective, it can reach a range of IP address, and to reach these range of IP address at once, it can send the data at the broadcast level, right? At the if it sends the data at the broadcast address, all the IP address in that range of IP will be receiving that data. That's why Ethernet considers Ethernet interfaces as broadcast interfaces. All right. Then loopback. Loopback interface, and OSPF considers it as a stub interface. Stub interface. And we will come across this stub interface a lot in real time and also in our future discussions as well. So what is a stub? Stub you can think of as a terminating interface or a terminal interface, meaning that after this there is no path. There is no path, right? We have Mumbai terminus, right? We have Chennai terminus, and in Kolkata also we have a terminus, right? That means that's the end of the track. After this, there is no track. Similarly, loopback an OSPF. OSPF considers loopback IPs as a stub interface, wherein after that there is no path. Okay. Now, why are these interfaces important to understand? Is because when we are checking from a troubleshooting point of view, this is important to understand. And where will we come across these interfaces in OSPF? I will tell you when we start the practical. All right. Now, let us go ahead with OSPF on serial interfaces. OSPF on serial interfaces. All right. Now we have two routers, R1. I'm just considering two routers, R1 connected via a serial interface to R2. This is how a serial interface is denoted in topology, like a Z, okay, or a lightning bolt. So it is usually denoted like this in a serial interface. R1's IP address or interface IP address is 12.0.0.1 and R2's IP address is 12.0.0.2. Right. Now, when we enable OSPF, or if I have to configure OSPF on this particular interface or router, how do I do so? What I will do, I will go into the configuration terminal. Okay. Then in the configuration terminal, I will say router OSPF. Okay, meaning that I'm saying that on this router, I'm enabling OSPF. And then I will write a number. That is, for example, OSPF 1. This 1 is called as the process ID. Process ID. This is what it means. Process ID. Router OSPF 1. Process ID. Okay. Now, what is a process ID? Let me open my task manager. So you see, on my task manager, you can see there are so many processes that are running. Firefox, Microsoft OneNote, Task Manager, Zoom meeting, and there are so many different other processes that are running on my system. Okay. Obviously, in the background, these processes have some kind of number or ID, right? When we are talking from a RAM perspective, right? How much CPU utilization is happening? You can see 53% memory is consumed by my system. Okay, out of that, these many MBs of RAM is being utilized by Firefox. Right. So what is happening? It is basically telling that Firefox is out of this 53% of memory that is being utilized, 1285 MB of memory is utilized by Firefox. So if we are a Linux expert, we can check the processing of Firefox through a process ID. It has an ID for it. Similarly, Microsoft has its own unique ID. Task Manager has its own unique ID. Zoom meeting will have its own unique ID. Similarly, all these processes will have their own unique ID. So router OSPF1, when I say that, I am telling the router, okay, please remember, now I am talking from a very, hardware point of view. Okay, we're not talking from a network point of view. Whatever I'm explaining right now is from a hardware point of view, not from a networking point of view. Router is a networking device or an electronic device. Router is an electronic device. Okay, which has its own intelligence as well, right? It has chips, it has motherboards, it has ICs on it, right? It has ICs on it, it has a fan, right? It's a whole box. Okay, I've shown you the pictures of a router. How does it look, right? So if it has a motherboard, that means it will have a memory. correct? It will have a memory. And if it has a memory, then we are talking from RAM perspective, from a RAM perspective, right? Now, when I enable OSPF on the router, when I enable OSPF on the router, I am telling the router that I am enabling OSPF inside you. Okay. Now it is your job to create a or create a memory or space for OSPF inside your chip. Okay. Inside your memory, you need to create some space for OSPF and give that space an ID of 1. An ID of 1. This is what router OSPF 1 means. I am telling the router I'm enabling OSPF inside you with a process ID of 1. So if I have to search for OSPF, I can search using the process ID in the memory as well. Okay. Now, whatever I explained you about process ID is not important from a networking point of view, but I had to explain it. What is a process ID? All right. Any questions?
Hi, sir. Actually, there are multicast addresses, right? 224.0.0.5
Hold,
and
hold on, give me a minute. Your voice is too low. Yeah, now speak, please. Yeah.
yeah, actually there are two multicast addresses,
Huh.
224.0.0.5 and 06.
Huh.
So how both are different and where it is used?
Yeah, I'll come to that part. We will
Okay.
come to that section
Yeah.
later.
Okay, sir.
So router OSPF 1. Okay. 1 is a process ID, and it's, as I said, it's a process ID. That means I can run multiple processes of OSPF. Okay. When we will do the practicals, I will show you that from 1 up till this, there is a number. I don't know what the exact number is. It's a huge number. You can have so many different OSPF processes running on a inside a router. Just like my task manager, you can see there are 16 Firefox processes running. There are different processes. On my laptop, I have a Firefox running, but I have 16 different processes of Firefox running. Similarly, you can have multiple OSPF processes running on a router as well. Okay, so
So those
OSPF
will not
1, 2,
collide anytime.
no, they will not collide. That
Like
is why
same
you have a
Firefox has
process ID.
different tab.
That is why you have a process ID to
That is a different,
differentiate them.
completely different memory, completely different memory location. So
Completely different memory. Yes, exactly. You're right. Completely different memory. All right. Now, once you do this, what you do is router OSPF 1, right? And then you write the command network 12.0.0.0 0.255.255.255. Okay. Area 0. For now, ignore this part. We will talk about area when it's the right time to talk about area. But please remember, we have to use this particular command, area 0. Okay. In short, let me explain you what an area is. Area is like these two routers belong to the same region. That's all. They belong to the same area, and that area number is 0. That's it. Okay. For now, just understand from that perspective. And this is a syntax. This is the syntax for OSPF. You cannot omit area 0 in the command. Area 0 is a syntax in this command, right? And now it's the part. It's the interesting part that we are going to learn today. Give me a minute. Someone is at the door. Give me. Okay. So now this particular syntax in OSPF, okay, has two purpose. Has two purpose. Okay. First, First is to advertise the network. First is to advertise the network. What network is it advertising? The network which we have mentioned in the command lines. To advertise that particular network. And why is that advertisement needed? Okay, why is that advertisement needed? So that it is populated in R2's routing table. Okay, please understand what is routing. What is routing? We are using in order for the router to route a particular traffic, that particular network should be present in the router's routing table, right? So over here, what we are doing is with the network command, we are advertising this particular network to other routers so that they, in their routing table, this particular network is present. That is the purpose of network command, to advertise the network. Okay. Now, over here, today we'll concentrate only on the first part, the first purpose, advertising the network. Okay. Then tomorrow we'll talk about the second purpose. I'll talk about the second purpose, or let me just write that down. Second is dynamic discovery of neighbors. Dynamic discovery of neighbors. We'll talk about this second purpose tomorrow or the next week. So today we'll talk about the first one, advertise the network. Okay. Now, if you see here, we are using this command network 12.0.0.0, then 0.255.255.255. And you may notice that this looks a bit odd. Okay, this looks like an address mask, but the writing convention of this particular address mask is different. We usually write it as 255.0.0.0. However, this is just the reverse. 0.255.255.255. So it does not fit well, right? The reason it does not fit well is that, first of all, OSPF has been designed like that. Okay, OSPF has been designed like that. Second thing, this particular part in the network command is not called as an address mask, but it is called as a wild card mask. It is called as a wild card mask. Okay, and wild card mask is always written in this format or in the opposite form or reverse form of address mask. So 255.
So why do we need two different masks there? One is we have already.
As I said, that is how.
The IP
As I said,
mask is
that
there.
is
So why we
how.
need again one more?
As I said, that is how OSPF has been designed. Okay, so you will find this wildcard mask in OSPF, in every routing protocols like EIGRP, ISIS, even in BGP, you will find these wildcard masks written in this form only. They are not written in the normal form 255.0.0.0. They're not written in this. They're not written in that form. They're written in the opposite form. Okay, that is how they have been designed. Okay, and honestly, even I don't have that answer. Why are they designed so? Honestly, I do not have that answer. Okay, so here we usually write it as 12.0.0.0 and the address mask as 255.0.0.0. Correct. Now, to find the wildcard mask, for a particular address, mask, to find a wildcard mask, all you need to do is subtract the whole wildcard mask with 255 broadcast, 255.255.255.255. Okay, when you subtract, you will get 0.255.255.255. This is the wildcard mask for this address mask. So if I give you any other wildcard mask, address mask, sorry, 255.255.0.0. To find the wildcard mask for this particular address mask, all you need to do is subtract it with the broadcast address mask. What are you going to get? This is 0.255.255. Okay, this is not 2, I'm just writing 255 as 2. This is 250. So 0.0.255.250, right? Then the wildcard mask for 255.255.255.0 is going to be subtract everything with 255. So you will get 0.0.0.255. This is the wildcard mask for a class C address mask, class B address mask, and class A address mask. These are their respective wildcard masks. Now, if you are given any other IP address, or not IP address, any other address mask, not 255, any other address mask like 255.255.224.0. Now you have to find out the wildcard mask for this particular address mask. Very simple. Just subtract it with 255. 255.255. Okay. So over here, this is going to be 0, 0 dot here. It is again 255. Okay. This is 31. 31.255 is the wildcard mask. Wildcard mask for this particular address mask. So this is how you basically find the wildcard mask. Okay. So we understood what a wildcard mask is, how to find wildcard masks for their respective address masks. We now know the process. Okay. Now let us understand what is this particular command, or this particular command in the syntax basically doing. Okay, let us try to understand that with a good example and a diagram. Okay. And give me some time. Give me a few minutes. Let me open up a PDF. Now, okay, so I hope you are clear with what a wildcard mask look like and how to find the wildcard mask for the respective address masks. Okay. Now, what is the significance of this network command and the wildcard mask combination? We have to understand that. Okay, I have mentioned it is used to advertise the network. But how is it that the network ID and the wildcard mask are advertising the network? Let's try to understand that. Okay. So we will be using this diagram and the network commands that we see here. And we are talking from the perspective of R1. Okay. We are talking from the perspective of R1 over here. Now, okay. So the first command, it says network 10.1.0.0, 0.0.255.250. So 10.1.0.0, 0.0.255.255. Okay, this is the network ID and the wildcard mask combination. All right. Now, what OSPF does, as I said, it advertises the network. Now, from OSPF's perspective, how is it advertising and where is it advertising? Let's try to understand. Okay, you just heard me saying two things. How is it advertising? The second, where is it advertising? Two things. We will try to understand this with these network command and the wildcard mask combination. So listen to this very carefully. So what OSPF does is, it will compare in the octets wherever there is zero. Wherever there is zero in the wildcard mask octets, it will just write down those values. So that is 10.1. Wherever there are zeros, it will just ignore those octets. It has completely ignored these octets. And the octets that it has considered are the first two octets, 10.1. Because as per the wildcard mask, the first two octets are 0, and that is what the OSPF is looking for. Okay. Now, with the wildcard mask, the first two octets are 10.1. Now, what does OSPF do with this network command and wildcard combination is that it will search for interfaces that have IP address starting with 10.1. Okay, read the statement carefully. It says the network command with the network ID and the wildcard mask combination searches for interfaces that have the IP addresses starting with that number, or in this particular scenario, 10.1. Okay. Now, what are the interfaces that start with 10.1 IP address? 1, 2, 3, 4, and 5. Okay. As I said, it will ignore the other octaves. Here you have 1.1, 2.1, 12.1, 13.1, 14.1. It is completely ignoring the last two octets. It does not care what the numbers are in the last two octets. It only cares for the first two octets in the IP address, that is 10.1. And it has found from R1's interface, it has found there are 5 interfaces that start with 10.1. Okay. Now, before I move on, are you guys with me till here? Any question?
Yes.
Here, Saugata, are you clear with this?
Yes, it's clear till now.
Yeah. Now, once it finds out the interfaces that start with 10.1, what OSPF does is OSPF will send, listen to this carefully, OSPF will send OSPF messages out of those interfaces. It will send OSPF messages out of those interfaces to the neighboring devices. So out of these 5 interfaces, it sends those, sends OSPF messages. It sends OSPF messages, and in those OSPF messages, it is talking about 10.1.0.0 network. It is talking about 10.1.0.0 network. So when the OSPF recognizes or identifies the interfaces that starts with 10.1, it sends OSPF messages through those interfaces and tell or talks about 10.1.0.0 network through those OSPF messages.
So router like two interfaces will have the same network?
Yeah, you can see here.
10.1.
See over here.
10.1.2. No, this mask is which mask? 24, 24 is there, that's why.
Yeah, /24. As I said,
That's why it
here,
is a 3.
no,
It is
no,
not
see
the,
here
the
it is
example
not,
you
it
showed
is
below,
not,
it
as I
is,
said, it is not at all considering the address mask. It is only considering the numbers that are present. The,
okay,
as I
not
said,
based
the
on the below mask. No, wildcard not below the.
wildcard mask is not address mask.
Okay, so that's why I got
Wildcard,
confused because below you showed 10, 100 and 250 or 250 this one. I thought based on that it is checking, but here it came as 10, 11. Every interface is having 10.1. Because it
Yeah.
is slash 24, that's why it is different, because 10.1.12, 10.1.13, 10.1.14, those are class
Correct.
C type, right?
Class
So
C
that's why it
type.
is taking.
Yeah.
So it is, so
So over here, as I said, the
so
wildcard mask doesn't the OSPF does not care about your address mask. Is it a class A, class B, class C? It does not care. Based on the
okay.
wildcard mask that we have mentioned over here, whatever mention we have configured, based on the wildcard mask, is it looks for those octaves in the IP address. And if it matches, it will send OSPF messages to those interfaces.
So it can be anything, like we can take class C networks there, and we can wildcard mask we can pass for class B like that, and class A
Yes,
also we can do. Okay.
yes, you can do that.
So based on the wildcard mask, it will select the networks, but not based on the IPs which is assigned to the interfaces.
Exactly, exactly, exactly. So with this, what is happening? It is sending information about 10.1.0.0 network, 10.1.0.0 network, okay, through these interfaces. It is not talking about 10.1.24 network slash 24. No, it is talking about 10.1.0.0 slash. Okay, because if you further segregate this slash 16, okay, if you further subnet it, it can go to 24 also. You can make it as slash 24 also. Correct. So slash 24 is a subnet or is a sub part of slash 16. That is why even if it advertises 10.1.0.0, it is not doing any harm. It is not doing any harm. Correct. I hope you're getting this point. All right. Now, why is it advertising? And what will happen with this advertising? What is going to happen is R2, in R2's routing table, 10.1.0.0 network will be populated. R3's network, R3's routing table also 10.1.0.0 will be populated. R4's routing table also 10.1.0.0 will be populated. Over here, whatever devices are present, okay, in their routing table also 10.1.0.0 will be populated. And when they are populated, it will be also populated with the interface that they received this message on. Okay, so it on R2's routing table, it will say to reach 10.1.0.0, I have to send the data out of gigabit 0 slash 1 slash 0. On R3, it will be gigabit 0 slash 0 slash 0. On R4 also, it will be gigabit 0 slash 0 slash 0. Okay, over here, whatever the receiving interfaces, that will be populated. That will be populated. So this is how OSPF is using the network command and the wildcard mask combination to advertise a particular network, thereby helping the other router to populate their routing table. Okay. If you are confused, it's okay. It's okay to be confused. We will look at different combinations of network command and address mask, wildcard mask, in order to understand this even better. But if you have understood till here, are you guys with me?
It's a little bit confusing with those masks.
Yeah. No problem. No problem. Okay. Let's
So,
look
sir,
at.
actually,
Yeah.
what I understand is there's a
Yeah.
difference between subnet mask and wildcard mask. Is subnet mask in subnet mask one is represent network and zero represent host, and here in the wildcard
Correct.
mask, 00, the numbers will be same in the 00. When it represents 255 255, it is changing. Like
Yeah. You
here,
can.
here if you see 10.1 is it is constant, but
Correct.
after that it
So
is
over.
changing.
Yeah. You can. That's what I said. It's just the
Hmm.
reverse of the address mask, but the working is different.
Yeah.
Okay, 0 represents network, 255 represents host in this part in wildcard masks.
Yes.
So from that observation, it is correct.
Mhm.
But the working of wildcard mask is different.
Okay.
Okay. Now, okay, it's okay. You guys are confused. I know. Let's look at few other examples. Okay. Next is 10. We'll look at this one. 10.0.0.0 and the wildcard mask is 0.255.255.255. Okay. So over here, as I said, wherever there is 0, it will mark that particular octet in the IP address and it will ignore the rest of the octets. And with this, it will check all the interfaces that have an IP address starting with 10. Again, that is all these interfaces. All these interfaces. And now it will advertise through these interfaces the network of 10.0.0.0 network through these interfaces. Through these interfaces, it will advertise the network of 10.0.0.0 to all the devices that are connected on that interface. So on R2, now R2 knows to reach 10.1.0.10.0.0.0 network, it needs to send the data out of gigabit 0/1/0 interface. So this is how OSPF is helping the other routers populate their routing table by advertising through OSPF messages. By advertising through OSPF messages. Okay, let's look at few more examples in order to understand this even better. Okay, leave this for now because it will be confusing. Let's go to this one. It is 10.1.13.0 and the address mask is 0.0.0.255. Okay, so wherever there are zeros, we will just write that number 10.1.13. It will ignore the last octet. So over here, what OSPF will search? OSPF will search for that particular interface which has an IP address starting with 10.1.13. That interface is this interface. So OSPF messages will be sent out of only this particular interface. And on R3, on R3's routing table, 10.1.13.0 network will be populated. And to reach this particular network, R3 needs to send the data out of gigabit 0/0/0. All the other routers, R2, R4, or whatever the routers are over here, they are completely oblivious, or they are completely unaware of any other network that is present on R. On R2's routing table, R4's routing table, and the routing table of these devices, they are completely unaware of any network that is present on R1. They do not know. So if any data comes over here for 10.1. Let's say 12.1, for example. For example, R2 does not know because R1 did not advertise it. Or let's say, for example, 13 network. R2 does not know about it. R4 will also not know about it. And these guys will also not know about 10.1.13. The only router that will know about 10.1.13 network is R3, because from that interface only R3 received the information of that network. Again, R3 will never know about 10.1.14 network, 10.1.12 network, 10.1.1 network, 10.1.2 network, or 12 network, or any other network. It will only know about 10.1.13 network only, because that is what this particular interface was about. Clear? I hope a bit of confusion is cleared with this particular example.
Yes, sir. Actually, if the routers are in same area also, it won't like advertise, right? If it is in different mask. But
Interfaces,
yeah.
yes. Yes.
Okay.
Okay.
So
Yeah. Go on.
actually, what I know is maybe I'm wrong or right. I don't know. There is a
Mhm.
OSPF adjacency process there, right? It will
Yeah.
advertise the OSPF adjacency. It will start doing adjacency process. But
Mhm.
if they are on same network, it will advertise, right, to each and every router.
Yeah. So, okay, I'll come to that portion later. Okay.
Mhm.
But just do remind me, probably in the next session, we'll talk about that adjacency.
Okay, okay, sir.
Okay, we'll talk about the adjacency. Okay.
Okay, sir.
But do remind me about this question during that
Sure,
time.
sir. Sure. Yeah, thank you.
Now, the next is this one 10.1.13.1, 0.0.0.0. Okay, wherever there are zeros, write that value 10.1.13.1. So over here, OSPF will look for the exact IP address, or not IP address, exact interface with the IP address of 10.1.13.1, and that again is this interface, and it will send OSPF message out of this interface to R3. And R3 will only know about 10.1.13.1 IP address. It will not know about 13.2, it will not know about 13.3, 13.4, or any other IP address in 10.1.13.0 range. No, it will only know about this particular IP address. R3 will also not know about this network, or these networks. So R3's routing table will be populated with 10.1.13.1 and the exit interface to be G000. Any question?
No, sir.
Saugata, yourself? Any question? Hello? Saugata, can you hear me? All right. I think, yeah, Saugata.
One second. Is it audible now?
Yeah, now you're audible.
Okay. Yeah. Actually, yeah,
Any,
it got on. Actually, yeah. No, no, that's fine. It's fine. Actually, here I started answering. I at home or something.
okay, any question?
That's fine. And only that this things are a little bit confusing between this selection of networks. At one network only it is sending in one side, and other router is not knowing that. So is it like that only? Like it will send for that particular network to one side of router and other network to other router? Because like everybody should know other, or it is like one network will known by one router like that.
All right.
Because
So,
see for
as
the
a,
10.1.13 it sent one side only, and 10.1.12 thing it send that side only. So that router 2 will not know where router 3 is then. Then router 3 will not
yeah,
know where router 4 is. So they will have
correct.
only that much thing. So will they
Yeah,
get
yeah.
anytime, or it is like only that like one path will be there separated out.
Okay. So, now, with the network command, okay, with the the purpose of that, the first purpose, as I said, the first purpose is to advertise the network. Okay, advertisement of network is based on the first thing. Please understand, is based on the combination of the network ID and the wildcard. Okay, and based on the combination of the network ID and the wildcard mask, OSPF messages will be sent based on the interfaces. Right. So for this interface or this combination, OSPF messages are sent to all the interfaces, out of all the interfaces, and hence R2. Okay, will know about R2 will know about 10.1.0.0 network, which involves 10.1.1.1 network also, 10.1.2.1 network also, 10.1.12.1, 10.1.13.1, and 10.1.14.1 network also. This comprises everything, correct? So R2 will eventually know about this network, this network, this network, and this network. Clear? That is how your OSPF is advertising about the network to other routers as well. Similarly, R4. Okay, R4 will also know about 13 network, 12 network, 1 network, 2 network. Clear? I hope this makes.
Yeah,
I hope I have answered your
this
question.
yeah, this looks like a supernet they are sending, like all different subnets, but they're combining it and sending at the top level. It is sending to everybody, so it
Yes,
covers
you can.
each of the networks.
Yes, yes, yes. You're absolutely right.
But in that case, how they will know which part of 13 is which side it is and 12 is which side? They will get the whole network, right? 10.0 they will get it. But how they will know 10.13 is which side and 10.14 is which side and 10.1 is which side?
Because okay, it received the information of 10.1.0.0 through this site. Okay, so it needs to send the data out of here. R1 clearly knows this interface belongs to 12 network, this is 13 network, this belongs to 14 network. It is R1's duty to forward the data as per the network. It is not R2's
Okay.
information. Okay, so let's say R2 gets that 10.1.13, it needs to send the data to 10.1.13.3, which is R3's interface. Okay, so 10.1.13.3 is a part of 10.1.0.0, correct? And to reach this particular network, it needs to send the data out of G000. So R2 will send the data to R1. R1, upon receiving this data, okay, in its routing table, in R1's routing table, it will have 3 different networks, not 3 different, many networks. 10.1.1, 10.1.1.0 network, 10.1.2 dot network, 13 dot network, 14 dot network, and 12 dot network. Correct. So it received the data for 13 dot network. Okay. And to reach any IP address in this 13 dot network, it needs to send the data out of this interface. So it will forward the data out of that interface and it will reach us. That is how the data flow will happen. Clear? Hello?
Yeah, yeah.
Okay.
It's
To understand this better, you'll have to,
the
revisit this
lab.
recording. Yeah, the
The one
lab,
plus
plus
have to go to the lab.
revisit the static routing lab as well. Okay,
Okay.
right. So in static routing, we understood that, the moment I configure IP address on this interface, R1 will automatically know about 10.1.13 network, correct? It will know
In
about any,
static was yeah, static at least we had the idea where we are sending it. So this will go out of this interface, this will go out of that interface. We
yeah,
manually did that thing. So now this is like combining something and sending. They were not combining, no. They were giving okay, this network will send this side. So because we know
yeah,
that network is behind router one, that we behind this.
correct, correct. Okay. So, uh, okay, I understand that confusion. Okay, but tomorrow we'll look at this particular network command and wildcard mask combination tomorrow. Okay, and then we'll proceed further. So, as I said in today's class, my purpose was to not purpose. My agenda was to give you the idea of the first purpose, advertising the network. How OSPF is advertising the network. Okay, and we just understood with that diagram and the different examples how OSPF is advertising the network to different routers and how different routers routing table is getting populated through those advertisements. Okay, now any problem understanding the advertising part,
It's clear.
how
Yeah,
R2, R3, R4, and the other routers tables, routing tables are getting populated.
yeah,
Any,
that is how the flow is going. But only the
yeah,
doubt is how the combination is happening. That is a bit confused. Maybe I
Yeah,
will go
yeah.
through this once again. So
Okay, yeah, yeah. That's what. So you will have to go through the recording, and plus the PDF that I've shared for the CCNA Volume 1 and Volume 2. This diagram that I took was from the CCNA Volume 1. Okay, CCNA Volume 1, right, which I've already shared. Right, so you can check the OSPF chapter, page number 474. Okay, and then you read through that, and you will understand how wildcard masks are basically work. Okay, and tomorrow I'll also do a practical of this particular scenario. Okay, and then you will have a better idea of how advertisement is basically work. Okay, so see you guys on Monday. Okay, again, if it is a 9 p.m. or 9:30 p.m., I'll let you know a few minutes before. Okay.
okay, sure. Thanks.